Number 25. If you pour 0.01 kilograms of 20 degrees Celsius water onto a 1.2 kilogram block of ice, which is initially at negative 15 degrees Celsius, what is the final temperature? You may assume whatever. Okay, so in this video, I'm going to take a shortcut, okay, in order to answer this question. If you want a detailed analysis of how to figure out what I'm going to take the shortcut of, please check out number 24 in this chapter. Okay, I went into excruciating detail there. So basically, I know that there's going to be a heat transfer going on. All right, I have ice at this temperature. I have some liquid water at this temperature. They told me the masses of each. And I know that, since this is warmer and this is colder, when they touch one another, this thing will heat up and this thing will cool down. The critical question is, will this ice cube melt fully, or will this water freeze fully? That's the question. And that's what the prior video went into a lot of detail on. The shortcut is that I'm basically looking at, I know the specific heat of ice is about 2090. I know the water specific heat is about 4184. So the heat capacity, relatively speaking, is about twice as large just in terms of specific heat, not including mass into that equation. However, though, the mass of the ice is 100 times larger than the mass of the water. The temperatures are relatively equidistant from the melting point, which is 0 degrees. So I know that, that this contains much more heat energy, or this can absorb, I should say, much more heat energy by getting to 0 than this can lose by getting to 0. So I know that the liquid water here will freeze. And this will not, the ice cube will not melt. Okay? So that being said, now I can start talking about the problem. So we know that we have the heat of the ice and the heat gain. The ice is gaining heat, right? This ice cube will be gaining heat over time. And this water will be losing heat. So that's a negative, okay? Negative of the water, right? The water's losing heat. Q is heat. So now since I know that there's a phase change involved with the water, and I know that there will be no phase change involved with the ice, I can now set up this problem. I know that I can break the Q on up into basically, let me do this. So Q, not Q, but basically all I'm going to be doing is now substituting this part of the formula in for Q, okay? So it's the mass of the ice times the specific heat of the ice multiplied by the change in temperature of the ice. And that will equal now the heat lost by the water. But remember, there's two things, as I mentioned, that will happen here. First, the water will go from 20 degrees Celsius down to 0 degrees Celsius. And then there will be a phase change. And then the solid will then be gaining some heat. The solid that the water produced now, right, the ice that coming from that water, will then also probably continue to lose some heat as well. Okay? So again, check out number 24, detailed discussion. So what I'm going to do here is the mass of the water times the specific heat of the water times the change in temperature of the water, plus then the phase change value, the mass of that liquid water times the latent heat of fusion, plus then, now we're talking about the solid piece. So it's the mass of that solid piece of ice now, but this mass of the ice came from the liquid water, which is the same as the 0.01 kilograms, right? Times then the specific heat of the of ice multiplied then by the change in temperature of that ice. And also, guys, don't forget that it's negative. You have to take that into account. So here, put that in brackets and put a negative there. Okay? Now all I need to start doing is plugging in the values. So what's the original mass of the ice part? Well, it's 1.2 kilograms, right? So let me leave myself enough space. 1.2. Specific heat of ice is 2090. That's looked up. Okay, 2090. That comes right from a table. 2090, and then times the change in temperature of that ice. So it's some final value, I don't know what it is, minus the initial, it's starting at negative 15, right? So there we go. Now, negative. Now start plugging in these values. So the mass of the water, right, is started at 0.01. So every mass here is going to be the same, right? Because we're talking about the same item. The mass hasn't changed. So now it's 0.01. multiplied by the specific heat of the water, which is 4,184 about. The change in temperature now of that particular water, well, to get it to the freezing point. So it started at 20, the final temperature is 0. That's an 8. Final temperature is 0. And the initial temperature started at 20. All right, so we're going to get that math. Plus now the phase change energy. But really, you can think about this as being a negative sign in here. The reason why is because you're losing heat, and this will come out to be positive. You can consider then anytime you're going from either gas to liquid or from liquid to solid, the phase change value will always be negative because it's losing heat. All right. So here it's going to be negative. So then the mass is going to be 0.01 multiplied by, now careful, that's in kilojoules down there, right? This is gotten from the table in the text. So this is 334, but I want to convert that into joules. So just multiply it by 1000. Okay. And since I'm running out of space, I'm going to just put it beneath now. I'm going to put this term. So the mass of the ice, that hasn't changed. It's the mass of that ice component now is still we're talking about this mass of water freezing. So now it's ice and now the temperature is cooling. Multiplied by the specific heat of ice, so that's 2090. And then the final temperature, we don't know what it is, and it had to have started at 0 though. Okay? Close the brackets. So now it's just math. All right, so let's do this. So 1.2 times 2090 is going to be 2508. All right, so this basically, I'm going to try to combine a couple of steps here. This combines into 2508, 2508, and then what you would do is distribute, right, them to each term. Okay, and this is really a positive here. So after you do all that math out, it's going to be then 20. Let me move down a little bit. 2508 TF plus 2508 times 15, and it's going to be 37,620. 37,620. That will now equal negative. All right, do this math. So it's going to be 0.01 times 4184 multiplied by then negative 20. So that works out to be negative 836.8. Negative 836.8 minus then, this should be 3,000 when you do this, right? 3,340. Okay. And then do this math over here, right? So it's going to be a plus sign. And then you're going to just multiplying this out. It should be 20.9, right? 20.9. And then TF minus 0 is just TF. So that's just TF. Okay. And now what I'm going to do is let's distribute the negative. All right, just so we can get rid of this bracket and stuff. So we got to distribute it to each piece. So basically this thing becomes positive, this thing becomes positive, and this thing would become negative. All right, so let me just now, oops, 1 second. Let me just now erase the bracket and clean this up slightly. We said that should become negative, right? Yeah, we'll just bring that down. And voila. Now all we have to start doing, I'll get rid of these positives too, since we really, well, not that one. And now all we have to do is start combining some like terms. Okay? So we're going to do 2508 TF plus then 37,620 will equal then, let's combine those two there, the 836.8 plus then the 3340. So this is 4,176.8 minus then 20.9 TF. All right, combining more like terms. Basically, I think what I'm going to do here is I'm going to add this term on, it doesn't really matter. I'll add this term on over to the left-hand side, combine it with the other TF, 20.9 TF. Okay, and then I got to get this term away, so subtract 37,620 minus 37,620. And then let's just add them together, right? So we got 2508 plus 20.9. So it's just 28.9 TF. And that will then equal, it's going to be positive 4176.8 minus now 37,620. So this is now a negative 33,443.2. Just divide out now this value from both sides, and then you get your answer, okay? So divide it by now 2528.9. And lo and behold, we get a temperature, final temperature now of about negative 13.2 degrees Celsius, okay? that is the final answer. And notice it does make sense, right? This temperature should have gone down, and it did. And this temperature, well, I said gone down. I'm thinking about negative. Technically, the temperature it increased, right? So apologize. The temperature was negative 15, then it became negative 13.2. Otherwise, it didn't make sense. That temperature increased, and then the water started at 20, and it went all the way down to negative 13.2, basically. So that should hopefully make sense. If you forget this negative sign over here, guys, if you forget to include this, you would realize your final answer wouldn't make sense. It would be larger than negative 15 degrees Celsius. And then it just, how could it be? How could that get colder? It can't. All right. So anyway, hopefully this helps, guys. Please remember to help us out and subscribe. And we look forward to helping you out with more problems. Take care.